Okay, so welcome back. It's 10:50. So now this is the second part of today's lecture, and what we'll do is that now that we have introduced artificial intelligence, went over a few concrete applications, try to define what it is, what it's not. We'll start with the content of the course itself, and the first thing we'll try to define is what is an intelligent agent, with a bit more formally, and what are the kinds of environment or how to properly characterize the environment in which they are behaving. Okay, so what you should basically, or how we will usually consider the agent in the environment is with these two boxes. So on the left you have a box which represents a system, which is the agent, and these systems come with some sensors, and these sensors allow the agents to perceive its external environment. So for example, concretely, this agent could be, I don't know, a robot, and the sensors could be cameras that that equip that robot. And then, of course, this agent is running some program, and this is the box that you have in the middle with the question mark. And how to implement this program will be the focus of this entire course. And of course, this robot not only observes the environment, but can take actions in this environment, and it can take these actions through actuators. For example, if the robot is on wheels, then it could move forward, backward, or turn right, turn left, maybe grasp object if it's equipped with some kind of gripper, some kind of arm, and so on. And then the environment is modeled in this case as another box. And usually, the knowledge that we'll have will depend on the task, but we'll see that that knowledge may only be partial. The environment could be static, could be dynamic, could be stochastic. We'll define all these things properly soon. So the agent will define it as an entity which perceives its environment through sensors and takes actions through actuators. This is what I just said. And the behavior of the agent will be described by a mathematical function, or like a function that you write in some program. And this agent function, also the policy, what it will do is it will map a sequence of percepts to actions. Okay. So that means at every time steps, you will receive some input information for the environment. This input information is called a percept. And at every time step, what you want the agent function to do, so the content of this box, is to decide on the action that it should take now. Okay. And so what is important is that this function behaves not only on the immediate current time step, but on the entire histories of all the percepts that you have received so far. Okay, and so this is why this is mathematically a function that goes from P star to the action space. So where P star is the power set of the set of percepts that you can perceive. So maybe to make things a bit more concrete and to relate to the kind of things you will do your projects on, let's just for now consider a very simplified Pac-Man world, okay, in which you would only have two cells, a left and a right cell. There is Pac-Man in one of them, and there is a foot dot in the other, okay? And everywhere else there are walls, and you cannot go outside this box, okay? And so, for example, in this world, an agent could, for example, have as percept the location of Pac-Man, and so, for example, whether or not it's is it in the left or in the right cell, and whether or not there is a food in this same cell, okay? And then the actions that these Pac-Man agents could take would be either to go left to go right, to eat the food dot, or simply to do nothing. And so one way to implement this function would be the simplest way, the most naive way would be to basically just build a table in which on one side you have a possible sequence of percepts. Okay, like you are in the left cell, there is no food, then you say that the action that you should take if you are in this state is to go right. However, if you are in a state where you are in the left cell and there is a food in this cell, then the action that you should take is to eat it. If you are in the right cell and there is no food, then the action that you should take is to go left. If you're in the left cell and there is food, you should eat it. And then, so this would be like for the first percept, but of course we want to map the percept sequences to actions. And so another possible sequence of percept would be like in the previous or in the first state, you were in the left cell, there was no food. And now in the current state you are still in the left cell and there is no food, then the action that you should take is to go right, and so on and so on. So this would work, and you could imagine that you would implement an agent in this way if the state action space is of limited size, but very quickly you can understand that the size of this table would explode as the number of possible states that you are in and the number of actions that you can take grow in size. And then as an exercise, I just want to I will not give you the answer today, but then consider the same exercise. So what about the actual Pac-Man? So what could be the percept that you actually receive in the actual Pac-Man game, okay? And what are the possible actions that you can take when you're Pac-Man? Okay, it's nothing difficult, but just to practice these notions, try to answer these questions yourself. But then, of course, okay, so these are the percepts, these are the actions that we could take. Now what we want is to build one of these agent functions. So a mathematical function or a program that takes as input a sequence of percept and then produce an action. And so there are infinitely many programs that would be such functions, but what we really care about is like the best of these programs, okay? And so one immediate question that we would have is, what is the optimal Pac-Man in the end? Okay, what is the right agent function that you should use or that you should implement? And basically then when you think about it, then it boils down to how do you actually formulate the goal of Pac-Man, okay? So for example, you could say that Pac-Man receives 1 point per food dot collected up to time t, okay? Or it receives 1 point per food dot collected up to time t, but also you penalize Pac-Man of 1 unit per move, okay? Or you penalize when too many food dots are left and not collected, or something else, okay? So this is something you have to decide. You have to decide what is basically the reward function, what is the performance metric. And once you've decided that, then the whole question is, can you implement an agent function which would maximize this objective, which would maximize this performance metric with a program which is at the same time small and efficient. Small because, for example, you don't want to write one of these huge tables. It's simply not tractable, and efficient because you could also maybe just enumerate all possible state action pairs and all possible future trajectories, but this is not efficient either. So what we'll care about is rational agents. So intuitively, what you should understand is that for us, a rational agent would be an agent that does the right thing, okay? And to define properly what is the right thing, we will define a performance measure, which will evaluate a sequence of environment states caused by the agent behavior. So if you start the agent in some initial state, and then you let it follow its agent function, you will generate a trajectory, so sequence of states. Okay, at every time step, you will run the agent function, produce an action, and that will result in a new state. Okay, and what we'll do is that, given such a sequence of states, we'll define a performance measure. Okay, which will be a number, which will tell us whether or not this was a good or bad sequence of states. Okay, and then we'll define formally a rational agent as an agent that chooses whichever action that maximizes the expected value of the performance measure given the percept sequence to date. Okay, so there are quite a few things to unpack here. So you want to maximize, so usually, we'll say that the larger the performance metric, the better. Okay. Then we have expected value. So that means we are actually uncertain about the outcome of our action, but on average, we want the performance measure to be as high as possible. But it may mean that, okay, we'll design some action, but this will not be successful, okay, because we are just unlucky. And then finally, given the percept sequence to date, that means we want to take into account everything we have observed so far from the environment, because this gives us some clues, some information about the environment, and maybe, and almost surely, this information will be useful in order to maximize even more the performance measure. So what is nice with this concept of rationality, is that if you are able to implement an agent, then everything will behave well. You will have maximized this performance. But what you should not confuse rationality with is first with omniscience, which is that if you have an agent which is rational, it does not mean that it knows everything about the environment. Okay, for example, if you play the game of poker, okay, even if you have a rational agent, so for example, another human player, which we could consider as rational sometimes, it does not mean that because it's rational that it is omniscience. Okay, it does not know the cards that the other players are holding. Okay. And this is true because percept may not supply all relevant information. Of course, if you knew these cards from the other players, you could make even better decisions, but you don't know them and you have to deal with that. And you have to deal with these known unknowns in a way which is rational. Okay, the second concept is that rationality is different from clairvoyance, which means that the environment in which you act may be stochastic. So the outcome of your actions is itself a random variable. Okay, so you can have some kind of certainty or uncertainty about what could be the plausible outcomes of your actions. Okay, and you should deal and you should make use of this uncertainty in order to define your rational behavior. But being rational does not mean that if you take an action in a stochastic environment, you will not know that you will know the outcome of the actions. Okay. For example, again with the game of poker, let's say when we distribute the cards, you don't know which cards will be distributed. Okay. Okay. Then rational, so this is different from successful. It's not because you are maximizing and you are the most optimal rational agent that you will always be successful. Okay. And again, the reason is that the environment may be stochastic, so you may just be unlucky and therefore, you failed at what you wanted to do, or you are facing an agent which is better than you. Because, for example, this agent has access to more information, which then gives it some kind of leverage, and such that it's always more successful than you are, and so on. But what is interesting is that by just having this very simple definition of rationality, if you try to be rational, then it will automatically lead to exploration. So the fact that you will try to collect information about your environment in order to reduce your uncertainty if there are things you don't observe. Also about learning, so you will try to learn facts about the world, the dynamics about the world if you don't know it, again in order to reduce uncertainty, and to autonomy, meaning that you will not, in this case for example, explicitly write a computer program that would do this or that in such and such situation. Everything will be learned in some kind of autonomous way by the algorithm. Okay. So before we talk about the different ways you could implement this rational agent, what is important to understand is that, of course, the implementation of this agent function will depend on the characteristic of the environment that you are in. Okay, and so basically the characteristics of the performance measure, your metric that you want to optimize, the environment, the action space, the percept, all of them together will dictate the techniques, the algorithm that you should use for selecting actions that are rational. Okay, and formally what we'll do is that we'll summarize all these things together in what is called the task environment. Okay, so we'll have 4 components in a task environment: the performance measure, the environment, the actuator, and the sensors. So as an example, if we take the example of a self-driving car, then the kind of performance measure that we would like to maximize is, of course, safety. We don't want to harm the passengers or to harm pedestrians outside of the car. Of course, we want to drive somewhere, so we should arrive to the destination, and maybe we should arrive to that destination as quickly as possible. And we have to do that while following the road law, the traffic law. Of course, maybe we want to ensure some level of comfort to the passengers. If you drive very aggressively, then this may not be that good for the comfort of the passengers, and so on and so on. So these are many things that you could try to maximize for when it comes to autonomous cars. It could be a set of all these things, it could be all of them at once, they could be weighted in different ways. This is basically up to you. Then we have the environment itself. So in this case, it's the real world. So but usually just the roads, so the streets, the highways, the traffic. So all the other cars that you find or transport that you find on the roads, the pedestrians. Of course, the weather conditions. If it rains, if it's sunny, if it's foggy, then this is quite important for you. In particular, I don't know, if it's raining or if it's foggy, then what you perceive from the environment is very different from the kind of images you would get when it's sunny. If it's raining, then the dynamics of the world is also different. If you brake, then it would take a longer distance to stop, and these kind of things. Actuators, which will be everything that you can take as actions in a car. So steering, accelerate, brake, horn. Maybe you want to speak. The car would like to speak to the passengers, show things, and so on. And finally, all the sensors that you can use to know about your surrounding environment or the inside environment of the car. And for that, you could use cameras, accelerometers, gauges, engine sensors, GPS to know your location approximately, I don't know, LiDARs and other technologies. Okay, and all of these things together define the task environment. And of course, now if we take this task environment, the kind of algorithm that we would have to use to implement an agent function which is rational would be quite different from the kind of computer program that would try to play Pac-Man, okay? Because the environment itself and all its characteristics are much different. As a second example, let's take the one of an agent that would do shopping on the internet. So everything would be virtual, but you could say that you want to implement an agent to achieve this task. And then there your performance measure could be, of course, let's say what you want is to let's say you are implementing a feature to Google Assistant or Siri or whatever, and what you want to implement is something in which you say, okay, I want to buy a new bike of this brand, and that's it. And what you want the shopping agent to do would be to browse the web for different websites, shopping websites. And what we would like, for example, to maximize for is the price, or in this case to minimize, we would like, I suppose, the cheapest option, which meets all your requirements. Of course, you would like to maybe ensure that you have a bike of good enough quality, which is appropriate for your needs and which is efficient. Okay, and again, you could mix all these different measures together to have at the end a single metric. Then the environment, well, in this case, it would be quite different from the reality. It would be like the web, so all the current and the future websites, because of course you want your agents to continue to work properly even 1 or 2 years from now. And all the vendors, because maybe you would like to interact with them, ask some questions by email or by phone, I don't know, and also all the shippers to make the delivery of your item. Then the actuators would be what you display to the user, the web addresses, the URLs that you could follow when the agent has to browse the web. For forms that you could fill, so all the boxes, you can decide whatever you want to put inside. And then the sensors would be, in this case, for example, all the web pages that you receive, and this comes with text, graphics, and other scripts. Okay, so you see that there we have 2 different task environments. They are very different from each other, and you can, okay, if we want to write an AI agent for the first or the second one, it seems natural to maybe pick different algorithms to do that. Even though maybe they would share common pieces, they would be quite different from one another. Okay, so this was for the task environment. Now when it comes to the environments themselves, they can be of many different types. And so we'll go over a few of them. And the environment that we'll be dealing with will be combinations of these different properties. So the first one, which I already mentioned before, is whether or not the environment is fully observable or only partially observable. And by that, I mean whether the agent sensors give access to the complete state of the environment at each point in time. Okay, so for example, if you take games, the game of poker is only partially observable because you don't have complete access to the state of the environment. You don't know the cards that the other players are holding. But if you take the game of chess, then it's fully observable because you have you can look at the checkerboard and you have the complete knowledge. You know exactly the complete state of the environment at each point in time. Nothing is hidden to the players. Then whether or not the environment is deterministic or stochastic. And so by that I mean that whether the next state of the environment is completely determined by the current state and the action executed by the environment. And so in most real-world applications, this will be stochastic because the state by itself will be an approximation of the physical reality and will not have the full information. So some parts that we cannot describe will be modeled by stochastic processes. Another example of deterministic environment would be again like, I don't know, the game of chess, where when you put one of the piece on one of the cells, then you know exactly what would be the outcome because the rules of the game are just purely deterministic, and you know that if you move, I don't know, the queen one cell up, it will be there and nothing magic will happen otherwise. Then episodic versus sequential, which is whether the agent's experience is divided into atomic independent episodes, which is like, for example, again with games, an episode would be like a full game, and you could repeat this experience several times. So in this case, it would be episodic. And sequential typically would be like you have just a single instance of the agent in the environment, and that's it. And this is typically what we have in the real world. Then static versus dynamic. So whether the environment can change or the performance measure can change with time. And so usually you would have a dynamic environment. For example, if your actions can change the content, the nature of the environment itself, or when the performance measures can change with time, that would be dynamic. Then discrete versus continuous is basically whether the state of the environment, the time, the percept, everything that you have to deal with is either discrete or continuous. Okay. And we'll see in the first few lectures that we'll start easy with a discrete environment, but as soon as you make it continuous, then you need more advanced mathematical tools like probability theory to deal with that. Then single agent versus multi-agents. So are you alone in the environment as an agent, or are there other agents that with which you can also interact? So for example, in the case of Pac-Man, it's a multi-agent system because you have the agent Pac-Man itself, but you also have all the ghosts which are agents by themselves and which are running some policy. They have their own performance measure. For example, they would like to kill Pac-Man and they want to do that in some way which may or may not be rational. And then known versus unknown, which basically reflect the knowledge that the agent has about, I would say, the laws of physics of the environment. So do you basically understand the dynamics? Do you understand how the world evolves by itself? Or when you take, or do you understand exactly the consequences of your actions? And again, when you are in a control environment like a video game, this is known, but reality is more complicated, and in reality, the environment is unknown. We have some good approximation, but we don't understand everything about the world. Okay, so this is just again a list of different task environments, and a good exercise would be for you to answer whether or not they are fully observable, deterministic, episodic, static, discrete, single agents, or known. So I will just maybe go over a few of them myself. So poker, we talked about it already. So poker is partially observable. Is it deterministic or stochastic? It's stochastic because there is some randomness involved when you deal the cards. Is it episodic or sequential? In this case, it's episodic. You can play different games. Is it static or dynamic? It's static. The rules of the game do not change. Discrete or continuous? It's discrete. We are not describing the cards with continuous value. It's just one among the 50 possible cards. 52 possible cards. Single agents, multiple agents, it's a multiple agents because you are playing against other agents. Known or unknown, it's known because we know the rules of poker. Let's say, I don't know which one. Let's take the one of medical diagnosis. So is it fully observable or partially observable? In this case, it's partially observable because like a doctor or an agent that would try to do some diagnosis does not have access to the entire state of a patient. Is it deterministic or stochastic? Depends how you model the world, but I would say it's stochastic because there are things you don't understand but you can approximate in a stochastic way. For example, if you give a treatment to someone, you cannot predict with 100% certainty that this treatment will have the effect that you wanted it to have. Even though in reality, maybe there is some deterministic process which is there, but since you don't have access to the full, to the entire space, there are things you don't know, and you can approximate these things with stochastic processes. Is it episodic or sequential? Well, you could say it's episodic if you're a medical doctor and if you make a diagnosis to several patients. Is it discrete or continuous? I would say it's mixed. There are maybe features that you can collect about patients, like whether it's a male or female, the weight, the pulse, the heart pulse rate, and these kind of things. Some are discrete, some are continuous. Single agents, multiple agents. You could approximate that as a single agent, because yeah, I think it's fine to say that. Known or unknown. Well, in this case, it would be unknown because again, medicine is not omniscient. There are still many open problems, and we have to deal with that. And then maybe let's say chess with a clock. So is it fully observable or partially observable? In this case, it is fully observable. Is it deterministic or stochastic? It is deterministic. Is it episodic or sequential? It's episodic. You can play several times the game. Is it static or dynamic? In this case, it's dynamic because your performance measure will evolve with time because there is a clock. So that means if the delay expires, then you lose the game. Is it discrete or continuous? It's discrete. Single agent, multiple agent, it's single agent. Known or unknown, it's known. And again, this is something we'll ask you during the project. What about Pacman? So can you say if it's fully observable, deterministic, episodic, static, discrete, or single agents or known? Okay, so now we've described properly the features, some of the characteristics of the environments. Now let's talk about how to actually implement these agent functions. And so I will just, in this here, will give you some, like, I will sketch, broadly speaking, how to do that in different ways. And then the content of the following lectures will be about actually doing these things in all the gory details. That we'll talk about later. So the job of AI is basically to design an agent program that implements the agent function. And this program can be implemented in many ways. We have seen one already, which is to have like these lookup tables, but the problem is that they can grow very quickly in size. So this is not something tractable for anything useful. Or with rules, or with search algorithms, or with learning algorithms. So the first category of agents that we'll consider are known as reflex agents. And basically, it's agents that will take actions based on the current percept and maybe on some memory that they have. And only from this knowledge, they will decide on an action to do. And what is important is that these reflex agents will not anticipate the consequences of their actions. So it might be that their reflex actions are good in maybe 90% of the cases, but in 10% of the cases, they will just fail. Okay. And so, for example, if in this case you have these little agents, and the goal of these little agents is to grasp this apple, then because usually there is no hole in the environment, the action should be that if you see an apple, you should just get closer to the apple, and that's it. Of course, you can see that very quickly there are limitations, because you should have anticipated that given what you see about the world, and if you go forward too many times, then eventually you will just fall, and you will never ever grab this apple. So reflex agents choose an action based on the current percept and maybe some memory that they have internally. And this memory is basically a model of how the world, a model of the world's current state. Yeah, so I will go back to that. And so they may have a memory which is like a model of the world current state. And what is really important is that they do not consider the future consequences of their actions. They only base their decision on the present and on the past, but not on the future, or the hypothesized future. And so in this category of reflex agents, you might have several versions, from a naive to a more complicated version of these reflex agents. One would be what is known as simple reflex agents. Okay. So these simple reflex agents, what they do is that they get as input some information through their sensors, and this give them some information about what the world is like now. Okay. And from this percept, what they do is that instead of implementing a huge lookup table, what they do is that they compress this table through what is known as condition action rules. So we'll just map set of percepts to a condition, and given this condition, you have decided that you should take this action. Okay, so it's very simple. So in text, that means simple reflex agents select actions on the basis of the current percept, and when you do that, for this version of the reflex agents, you ignore the rest of the percept history. So for this simple reflex agent, there is no memory involved. And then you implement this mapping condition to action by having rules that will match the current percept to a condition. Okay, and then from this condition to an action. And this rule will provide a way to compress this function table. Okay, then for example, if you are considering the program that would drive a car, an autonomous car, one way to implement one of these simple reflex agents would be if a car in front of you slows down, then you should brake. Okay, and so the condition would be there is a car in front of me slowing down. Okay, and this condition can be mapped to several percepts. For example, the color and the model of the car which is in front of you is totally irrelevant. Okay, and so there are different pictures of cars that you could see before you, but as long as this corresponds to a car and it's slowing down, then you should brake. Also, other things that are totally irrelevant, like the music on the radio or the weather, are all irrelevant when you have to take this action. Of course, this will only work in an environment which is Markovian. Okay, which means that in an environment such that the correct decision can be made on the basis of only the current percept and nothing else. And that means, or another way to say that is to say that this simple reflex agent can only work in fully observable environments. Now, of course, the percept that you collect may not give you complete access to the state environment. And so maybe you should remember what you observed before in order to reduce the uncertainty that you have about the environment. So this is what is implemented when you add a memory to these reflex agents, and what we call them are model-based agents. So there is a discussion in the chat. I will come to it later. I think it's interesting. It's about the game of chess. I will do that at the end. So these model-based agents, what they have in addition to these condition action rules that we still have at the bottom here in the picture, is these things that you have at the top left. And so the memory will basically maintain some kind of state or belief state that you have about the world. So you think that the world is in this state, and so that means you have had to decide on a representation of the world. Okay, and when you already do that, you are making an approximation. Okay, and then so that means you can use this state to and you can update this state as you collect more and more percept, as you observe more and more about the environment. But to properly then narrow down all the possible the possible actual configuration of the environment, which you do not observe directly, what you should have also is a model of how the world evolves by itself, and also a models of what are the consequences of my action. Okay, and when you have all these things together, then okay, you can maintain some kind of state, which may be approximate and uncertain, but still you have some now additional information. And then the story is the same as before. Now that you will not map a percept to a condition, you will just map, you will use the percept, what you collect with your sensor, to update the state. And then given a state, you will map that to a condition. And then from this condition, you will map that to an action. Okay, and then you will actually take this action. So this memory allows model-based agent to handle partial observability of the environment by keeping track of the part of the world they cannot see now, but that they may have observed in the past. And the internal state of model-based agent is updated on the basis, as I said, of a model which determines how the environment evolves independently of the agent and how the agent's actions affect the world. And so, of course, for this to work properly, you have to have an accurate model. But if you do have, provided that you have an accurate model, then this can be very relevant and really result in much better agent than just simple reflex agent. So an issue with this implementation or this approach is that you still have these condition action rules, and this may not be something easy to define because usually what you will define is like a goal or performance metric, and so the immediate action that you should take given a condition usually are not directly related to the long-term goal that you would like to maximize. So properly defining this thing explicitly is usually difficult. So what you could do instead, a different version or different approach is known as planning agents. And so there, what you want to do is, in addition of using the current percept, the past percept to make a decision, you also want to anticipate what would be the consequences of the action in order to take to decide on the immediate action that you want to do. So for example, there again in this same illustration, instead of directly taking an action which is jumping, maybe you should anticipate for the different way you could jump, and for example the strength that you should apply, the forces that at which you should jump, such that you will reach the apple and you will not fall into the hole. But to do that, you have to anticipate what would be the consequences of your action. And of course, you can only do that up to some level of certainty. So basically, planning agents, they are different from reflex agents because they ask the question, what if? What if I do this action? What will be the consequences? And therefore, is it really a good action? Okay. And then from this hypothesized trajectory, they make decisions. Okay, but for that again, not only they must have a model of how the world evolves independently of them, but also in response to their actions. And finally, they must formulate a goal. Okay, so they must define exactly what they want to achieve, which is like the long-term objective and not explicitly the immediate action that you should do in each condition. So in terms of diagram, it works as follow. It's more or less the same as before, except that now we have replaced these condition action rules by goals. And what we are doing now is that, okay, we maintain some kind of state about what is the world, what the world is like now. And to do that, we need to use the same component as before. But also, we will take into account what will be the consequences of the actions. And so to do that, you have to basically project to be able to simulate possible trajectories, so sequences of state actions. And in this hypothesized trajectory, then you can evaluate whether or not you have achieved your goal. Okay, and if you find the trajectory in which your goal is achieved, in which your goal is true, then what you can take as action is the first action of that sequence, of that trajectory. Okay, So this is different from reflex agent in the sense that we are explicitly now exploring what will be the consequences, and we are using this exploration as a way to not have to explicitly make this lookup, this matching between condition and actions. We just explore a set of future trajectories, we'll assess whether or not the goals are achieved, and then if we find one of them, we may find several of them actually, then we'll take the first action of one of these sequence. Okay, and then we'll repeat over and over time steps. So the decision process is like this. You generate possible sequences of actions, you predict the resulting state, and then you assess the goals. You assess your goals in each. And then a goal-based agent will choose an action that will achieve this goal. Okay, so this is more general than rules that makes them easier to implement and easier to implement on tasks that are complicated, because the goals that you have, they are rarely formulated as explicit condition action rules. Okay. However, now, okay, don't have this problem anymore, but we have another problem, which is how do you find sequences of actions that will lead to a state in which the goal is achieved? This is itself difficult, but what we'll see algorithms to do that, and so this will be the topic of lecture 2 and 3 when we talk about search algorithm and planning algorithms. Okay. So for example, in the case again of the autonomous car, what's one of the goals that you could formulate is whether or not the car has arrived to the destination. Okay. And given this goal, now you can hypothesize about different routes that you could take, and then among all the possible routes, you only select the one to which, such that they correspond to trajectories for which you arrive to that destination, and then you take the first action for one of these sequences. But of course, when I describe it like this, you realize that there could be many different routes leading to a same destination. And maybe some of these trajectories are better than others. Okay? So it's more than just having a binary goal. It's also, you can basically rank all these trajectories with respect to each other. So, and formally what we have is that you can score this trajectory with what is known as a utility function, which will say that, okay, this is a sequence of state action pairs, a trajectory, an hypothesized trajectory, and not only I can assess if whether my goal has been achieved, but I can also score this trajectory, because maybe some will be shorter. If we take the example of the car, of course you want to arrive at the destination, but you want to reach destination as fast as possible. Okay, and the length basically of the trajectory could be an example of such utility. Okay, and so the last, or no, not the last, but then when it comes to planning agents, you have the goal-based agents, but you could upgrade them as utility-based agents. And so they work more or less the same as before, except that you will consider all possible trajectories, and then each of them you will assess them through your utility function, and then you will pick the first actions of the trajectory for which the utility is the highest. Okay? And the reason we want to do that is because goals are often not enough to generate high quality behavior. Like with this example with the car, there are many ways to arrive to the destination, but some are quicker or more reliable. Okay? So we want to go beyond this binary assessment of performance. And having a utility function allows us to precisely do that. Okay? And now that we have this formalism, then we can go back to what we were talking about when we were describing rational agent. Basically, what we'll try to implement in this course is a rational utility-based agent that chooses an action that maximizes the expected utility of its outcome. So I will answer. I see all your questions in the chat. I will, since I have just a few slides left, I will just go until the end, and then I will answer them after that. Okay, so and finally we have learning agents. So in everything I've talked about so far, you need basically a model of the world. And for these agents to work properly, you need a model which is accurate, which is a good approximation of reality, at least with respect, or at least a good approximation which is sufficient for the kind of goals that you have. And of course, this may itself be quite difficult to have in the first place. But what you can do, instead of first thinking for very long and then defining this model and then implementing this model in your agent function, what we can do now is to have agents that would be capable of self-improvement. So this is what we call learning agents. So these are agents that are able by themselves to figure out models of the world. So they are able to learn what would be the consequences of their actions if they do this and that, and how the world evolves. And they can manage to do that from the observations that they collect and from actions that they would take. Okay. And so in terms of the diagram, what you see inside the left box is the same as before, at least for the part on the right. We have sensors, performance element, actuator. Everything we have talked about so far was about how do you actually implement the performance element. It's something, it's a component which has as input a sequence of percept, do something which may or may not be fancy, and then decide on an action. But what we'd like to do is to be able to improve this box, the performance element, as we observe more and more the world. So to do that, what you can have is to have a learning element which would be able to change the content of the performance element. Okay, and you would be able to do that because you collect feedback from the environment. Okay, for example, I don't know, one example would be again the one of a car, and it tries to learn whether or not it should steer to the left or to the right. If you quickly, for example, turn left without telling the other the cars following you, then I'm quite sure you would be honked, and you can use this feedback that you received from the environment to then maybe figure out that maybe this was not such a good thing to do because the feedback is negative, and therefore you should avoid doing this kind of actions. And you learn basically that, okay, by just trial and error, that okay, you discover these kind of regularities about the environment. Okay, and then you can use that as you collect more and more observations to refine your models and then to plug them into the performance element. Of course, when you are like passively observing the environment, this may take some time to observe what are really the relevant bits to figure out precisely the environment. So if you want to be really fancy, what you can add is a problem generator, which will try to identify the regions of your model for which you are uncertain, for which you cannot predict very well what would happen if you were to take this or that action, and then to do experiments. So you would explore, you would add mechanism in your agents to sometimes explore things that you don't know much about, just to see how the environment would behave, and then use these observations that you collect then to refine your own model. So you would explicitly probe yourself, your lack of knowledge about certain part of the world. And then if you run this loop over and over, then your agent eventually would be capable of self-improvement. Of course, this all depends on how you actually implement these three other boxes, but just in an abstract fashion, this is how it could work. Okay, so as I said, these learning agents are capable of self-improvement. They can become more competent than their initial knowledge alone might allow. They can make changes to any of the knowledge components, so learning how the world evolves, learning what are the consequences of their actions, and also learning the utility itself for their actions through rewards that they collect through this feedback component. Okay, and this is the example I was telling you about making a quick left turn, and then the learning element, the critic would observe shocking language, for example, from the other drivers, and then would inform the system that this was actually a bad action. And then the learning element would try to modify the performance element to avoid reproducing this situation in the future. Okay. And then with regards to the problem generator, so you want to identify areas of behavior in need for improvement and therefore suggest experiments to carry out. So for example, one would be to try out the brakes on different surfaces in different weather conditions, because the distance that you need to stop would be different if it's raining or if the roads are dry. Okay, so to summarize what you've seen in this first lecture, so an agent is an entity that perceives and acts in an environment. Typically for us, this will be a computer program, but you could put that in a robot also. The performance measure evaluates the agent's behavior, and rational agents will act so as to maximize the expected value of the performance measure. Okay, so we have to define a performance measure, and then a rational agent will try to maximize that. And we don't care again how they're actually doing that, as long as they maximize it, we'll say they are rational. Task environments will include performance measure, environments, actuators, and sensor, and all these things can vary along several significant dimensions. The agent program effectively implements the agent function. The design is dictated, of course, by the environment in which you're evolving. Then simple reflex agents respond directly to percept. Then we saw model-based reflex agents, which would maintain an internal state to track the world. Then we saw planning agents when we talked about goal-based agents that would act in order to achieve a goal, usually a binary goal. And then you could make this better by having utility-based agents that would try instead to maximize their expected performance, which you can evaluate through some utility function, which would evaluate the whole sequence of state action pairs. And finally, all agents are able of self-improvement through learning. Okay, so that's it for today. If you have more questions, please put them in the chat. So I will answer the one that I delayed for the end. So one of the first questions was, is the chess not a multi-agent? There is 2 players. So of course, chess is a multiplayer agent. Maybe I said it was single agent, I don't remember, but it's a multi-agent game. You have 2 players. And if you know the weaknesses of your opponent, then you should exploit that in order to be better. But I see the discussion. You should not, playing against a lower elo player should not change the way you play. Counting on the mistake of the opponent is not a viable strategy. I kind of disagree with that. So if you are able to predict how the agent will behave, then that gives you leverage, and you should exploit that. And if you know that the agent is not optimal, but you cannot predict how it will play, then I agree. Then you should just assume that your opponent is playing optimally, and therefore, yes, in a sense, you could say that the fact that you're playing against someone is irrelevant. But these are things we'll talk about later. Maybe we can play. So planning and goal-based agents are the same. So planning agents is like a more general family of agents, and you have several implementations of planning agents. The first one is goal-based agent, and the second one would be utility-based agents. Will theory lectures will be in replay? Yes, I will edit the videos and I will publish them in the afternoons. Are the projects to be made by groups or solo by groups? Would self-modifying code be a solution for learning? Yes, it could be, but this is not usually how we are doing things today. What we do instead usually is that these models, at least today, they are usually implemented by neural networks, which are models with tons of parameters, millions or more of parameters. And when we say learning, usually we mean, at least in this context, updating the parameters value of these neural networks. And in a sense, if you view a neural network as a program, computer program, you're actually modifying the computer program as well. But in a way which is quite different from you would maybe picture if we are talking about, I don't know, Python program, and what you want is the program to change itself. What is the difference between deep learning and machine learning? So yeah, you could say that deep learning is a subset of machine learning. It focuses on basically models that are made with neural networks. And machine learning is larger than that. It also includes other kind of techniques that you can use to solve the same problems. In a game where the AI has to make the user believe that it is a human, can this AI learn trickery? What is the AI doing? Maybe, yes, I suppose the AI could learn this trickery given enough data. And yeah, as long as you give feedback and at some point the agent is able to figure out some really relevant information, then I suppose yes. Yes. Okay, so I think that's it for today. So the next lecture will be shorter than this one. So we actually went over 2 lectures today. I think the following lectures should take between 2 and maybe 2.5 hours. If you have more questions, you can ask them in the comments. I think it's probably a good idea if everyone tries to use the comments so that we share the knowledge, and I will try, or you can try to answer each other questions. It's also a good exercise. So thank you for following, and see you next week.